All right, the next set of problems we're going to look at all involve powers of secant and tangent and products between those. So the first type of problem we're going to look at is one where the power of the secant is even and positive. All right, so power of the secant even and positive. So here's one we have secant to the fourth, an even positive power of secant, and then we have tangent cubed. So here we're going to save a secant squared factor for the du and convert everything else into tangents. So keep in mind, think about the derivative of tangent is secant squared, right? So we're going to save a secant squared factor, and then since it's an even and positive power now, when we save a secant squared, we'll still have an even power of secant, which we can then use a Pythagorean identity to turn into tangents. Right, so here's our example. We take that secant to the fourth, we factor out a secant squared. I've put it in parentheses here. I don't really need to. I just kind of wanted to sort of emphasize that that's where it went. And I have a secant squared left, and a tangent cubed is the same as what we started with there. Right. Then use the Pythagorean identity to turn the secant squared 3x into a 1 plus tangent squared 3x. Now I can distribute the secant squared 3x dx and this tangent cubed as a whole. I can distribute that entire thing to the 1 and to the tangent squared. So I get tangent cubed 3x secant squared 3x plus now the tangent cubed times tangent squared. It gives me the tangent to the fifth and secant squared. And now both of these can be solved using u substitution, right? So I can let u equal tangent of 3x, and then du ends up being secant squared of 3x. And the same thing with this. U is tangent of 3x, du is secant squared 3x. And then I can work through that, offset some constant multiples there, and I get my final answer using u substitution there. All right, now let's look at an example where the power of the tangent is odd and positive. Here's one where we have odd positive power of tangent, and the approach here is that I want to work toward using like a u equals secant of x. Okay, so I need to save a secant tangent x, a secant x tangent x for the du. All right, so this one, the process is the same. This problem is a little more difficult, a little more intimidating, because I have to get that secant x tangent x. So first I'm going to turn this denominator of square root of secant x into just secant x to the negative 1/2. And then I'm going to factor a tangent out of the tangent cubed. I'm left with tangent squared. I'm going to factor a secant out of secant to the negative 1/2. So when I do that, I end up with secant of negative 3/2. Alright, so I remove a power of secant, move it over here, so I have to subtract 1 from that exponent. Alright, so I could take a look at what would happen when I distribute that back in. Of course, I would add the exponents back up, I'd get my negative 1/2 again. So I've just factored out a secant x tangent x. This here is now my du. Right? So I turn this tangent x into secants. The tangent squared into secant squared minus 1 using the Pythagorean identity. Then I distribute the secant negative 3/2 here and here. And then I'm going to take what is going to end up being my du, that secant x tangent x dx. I can distribute that here and here, and I end up with two integrals. And now you can see here that I can use u substitution. I can use u equals secant x, and then my du is secant tangent dx. And again here I use u equals secant x, and my du is secant x tangent x. And again, using u substitution, I get this final answer with the plus c. All right, the last one we're going to talk about is if the power of the tangent is even and positive. So in this case, we're talking about an example where there's no secant factors. So tangent even and positive, there's no secant factors, and we're going to turn one of the tangent squared factors into a secant squared factor. So we're going to factor out a tangent squared. Whatever's left is just going to go here. This becomes secant squared minus 1. I distribute the tangent. So now this first integral is in the form that I want it. The second integral, I'm going to turn that into secant squared. And once I do that, now I can integrate this quite easily because I know that the antiderivative of secant squared is tangent. And this one I can use u substitution with u equal to tangent of x, and then the du is secant squared dx. And of course this minus 1 integrates just to a simple x, and of course it becomes plus 1 because I have the minus the negative 1 there. Right? So we haven't talked about powers of secant being odd and positive. If we come across problems like this, where secant has an odd and positive exponent and there's no tangent factors, you can just use integration by parts for that, and it'll work out fine. All right. Sort of the option of last resort, if all else fails, try to convert everything to sine and cosine, and then see what you can work out, see what kind of patterns you can see from there, and work that angle of it.